I will be talking about is a general introduction to why gravitational waves are important and why the detection is important. And then at the later part of the talk, I will go into what is interesting for me. So as you heard, like, I'm more of a relativist. So I'll try to show how from a gravitational wave point of view, we can test theories of gravity. So I'll just give you a brief idea about how this is done. Okay, but before we do that, let's go back. Let's take a step back. So when we talk about space-time, what is the first thing that comes to your mind? If you're like me, for me, time is like a clock which ticks regularly for everyone and everywhere. And it doesn't matter who you are or where you are, it's going to tick. And a space-time, from our school days, we know that it's just a three-dimensional Cartesian grid, which helps us to find a particular event at a particular point, at a particular instant of time. But in the last 100 years or so, we have learned that space and time can be in the same footing. And this comes from the theory of special relativity. And so you have the space-time, which is a fabric, with the space and time becomes a fabric in this space-time dynamics, and which helps us to understand the theory of gravity, which is a bit different from the Newton's law. So what we know from Newton's law is this magical attractive force, but that's not true here. What happens here is the masses create a curvature in the space-time, and the matter walks according to it. So what we know here is the space-time is not a stiff thing. It squeezes, it bends, and it can extend. And so it's not just it's a continuous process. It's not just it plays an active role in our space-time, in this entire evolution of our universe. So space-time is dynamic. Now, where do we get this from? And I promise there won't be a lot of equations, but I just wanted to give just one thing. There's one field equation in my slide from general relativity, which basically, what it actually says comes from the famous physicist John Wheeler, which says that the space-time tells matter how to move, and matter tells space-time how to curve. So with that, we are back to this picture. So now we know that these two bodies, which are here, the sun and the earth, they're attracted to each other due to the curvature they produce on this 2D green grid. So the bending of the curvature depends on the mass of the body. So you can see that the sun bends the curvature more than the earth. And the takeaway message from this particular slide is that when a binary system is rotating around each other, they create a perturbation in the space-time. And this perturbation, unlike what we know from a Newtonian point of view, is not instant. Okay? It propagates at a particular speed, which is the speed of light. And that is one of the basic assumptions of relativity. So now, going to the next slide, is if we have a perturbation which has a finite speed, which propagates at a finite speed, then this creates a wave. And here we see two binary systems orbiting around each other and propagating what we call is the gravitational wave. So here we are creating a dynamics in the space-time of the curvature. So you see basically two bodies moving around each other and finally collapsing, and that generates a perturbation in the space-time which propagates out. And this is what we will see that we observe by LIGO. So what this actually does, how do we measure it? The thing is this, for the experimentalists, this is what they need to know. So since this is an actual perturbation of the space-time, what it does is it basically stretches or squeezes the length. So if say there's a gravitational wave coming towards me, it will at one point stretch me in the vertical direction and squeeze me in the horizontal direction, making me taller and thinner. And in the next moment, that is after a period, it will do just the opposite and make me fatter and shorter. So this is exactly what happens. So to see it in a different way, if you have a freely falling mesh of particles in the form of a cylinder, as you can see in this figure, in the outer space, and you see the wave propagating along the axis of the cylinder, then what will happen, this squeezing and stretching, the impact will be what you are seeing here. So again, as I said, so what we actually measure. So let's take out of this mesh, let's take just one ring, okay? We take one ring, and the length of this, and the length that we consider here is the diameter is the radius of the ring. So what we see is the change in the length is proportional to the original length that we are considering. So here the original length is L. Now the gravitational wave passes through it, and it produces deformation. So what happens now is the change in length is, say, some delta L, which is proportional to this original length, okay? And this is defined by something which is called strain, and you will hear me saying this a lot and showing this plot a lot, showing plots about strains a lot, which basically means the change in the length to the original length. So as you can see, it's a dimensionless quantity, okay? And that is what the LIGO interferometers measure. So now everything is fine. We know what to measure. We know it creates what are gravitational waves. We know what it does. It stretches or squeezes the length or the distance. But where are these gravitational waves? If we know that accelerating bodies create gravitational waves, and there are many accelerating bodies around us, so why can't we see this? The answer is there are gravitational waves everywhere. The only problem is they are very, very weak. So again, I'll go back to my one equation slide, where now I'm going to say what this field equation or this Einstein field equation actually means. So the left-hand side of the field equation tells you about the curvature. So if you remember the quote, there's curvature and matter. So the left-hand side of the equation tells you about the curvature. The right-hand side tells you about the matter. The only problem is they are proportional to each other, and the proportional constant is very, very small. So it's very hard to bend a space-time. You need a lot of mass to bend space-time. And that's why gravitational wave is very, very weak. Now, let's try to get a hold of how weak it is. Just to give you, it's not to give you a lot of equations, it's just to give you some numbers so that you can feel the importance of why these interferometers are required and what kind of job these guys are doing. So let's take our very conventional gravitational wave source, which is a binary system. So anything can be a binary system, So say an Earth-Moon system, an Earth-Sun system. Here you can see two black holes orbiting against each other. So they do produce gravitational waves. Now, you have seen this quantity, which is the strain, which is the change in the length to the original length. And what happens is, it is inversely proportional to this capital R, which is the distance from the source to us, and directly proportional to the masses of these two objects, and inversely proportional to the distance between them, which is denoted by the small r. Okay? And the other thing is, which is a bit complicated, is the energy which is radiated by this gravitational wave. The take-home message is, if you have more massive binaries, and if they are closer to each other, they will start orbiting faster and generate more and more gravitational wave. Okay? So, as you know, whenever you learn something, you have to do a problem. So, let's solve a Earth-Sun problem. So here you have the binary systems, Earth and Sun. Your strain is of the order of 10 to the power of minus 26. As you remember, it's a dimensionless quantity. And the energy that has been radiated out, or the power, is that of 200-watt light bulbs. Okay? Now, you might think that's a lot, but you have to imagine that the entire mass of the Sun and the Earth is going to produce this small amount of energy. Okay, so now you can understand that it's very, very weak. Just to say one more thing is, when I'm saying 10 to the power minus 26, I'm observing it 1 light year away from this binary system. Okay, so now to measure this very, very small number, or very, very small strain, you need something. You need interferometers. And that's where LIGO comes into the picture. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. And as the name suggests, the basic technology behind this instrument is interferometry. So what happens is, a laser beam is shot, and it goes to, and it gets divided by this beam splitter, and it divides it into 2 perpendicular directions. And once it gets bounced by the mirrors here at the 2 arms, and then bounces back to the point they got split. And if this arm length is same, then the phase will work in such a way that there will be no output on this side. But say there is a gravitational wave coming in, and they squeeze and extend the arms a bit, and so the arm lengths change, and then you see a detection or the light coming out on the photodiode, and that is what LIGO detects. Now the signal that you can find here, that will be detected here, is converted into electrical signals, and from that it can be transformed into frequencies, and we will see that later. Okay. So the actual interferometers are much more complicated. So the LIGO currently has 2 interferometers, one in Livingston, Louisiana, and the other one in Hanford, Washington. Okay, so they are supposed to be clones of each other. So each of the arm lengths here are of 4 kilometers. Okay, and there's a lot of precise instruments and cutting-edge technology which goes inside, which tries to keep the mirrors and all those other optics and the tunnels in such a way that they don't get disturbed by us. So say if there's a wave in the Pacific Ocean, these LIGO detectors should actually observe it, but they are maintained in such a way that this doesn't affect them. So these tunnels, these long tunnels, are the best vacuum that you can ever get. The lasers are the best lasers that you can ever get. So there's no scattering of light when the light travels here because it's complete vacuum. And all the other instruments which goes into it, which boggles my mind and I really don't understand most of it, keeps the system perfect. So that what we observe is the gravitational waves coming from extraterrestrial sources. Okay, so now that we were all ready for this, we were all ready for this, and by ready I mean, sorry. By ready I mean there were 1,000 scientists, more than 1,000 scientists working over 16 countries. That when the first detection happened on 15th September, on 14th September? Yeah, 14th September 2015, we were all ready for it. So this is what actually happened. About 1.3 billion light years away, two black holes of around 30 solar mass each, they inspiraled and merged, and that is what we observed at Earth. But this is not a very simple process. This entire inspiral that you just saw was going on for millions of years, and then what we observed was just the final milliseconds of this particular event. So basically when this event actually happened, there were multicellular organisms which were growing on Earth. And then like 15,000 years ago, when this wave was just at the outskirts of our own galaxy, humans came into existence. And then about 100 years ago, Einstein predicted that we will see something like this, and then we observed this. And just exactly, so I'm just going to show this simulation again. So these are two black holes which are orbiting for say millions of years, and then finally they radiate gravitational wave, which we don't observe because we are not in that sensitivity region. But then they radiate gravitational energy, lose energy, combine, and form another black hole, which is around a 60-something solar mass black hole. What happens is they radiate out energy equivalent to 3 solar mass. So yeah, and it formed a black hole which is of the order of 60 solar mass, and it ejected out a mass of around 3 solar mass. So it was one of the violent events that can happen. So you can, if I want to give you a number, it is basically brighter than all the stars of all the galaxies of the visible universe at that point of time. Okay, so Earth felt it, and we observed the gravitational wave. So now what I just said is not. It might look like a fantasy, but it is not one. And we know this because we have the data and we have observed the data. And as I mentioned before, when you see the data on the photodiode, you can transfer it into electrical signals, which is basically in the frequency band, or the audible frequency band. So what you will see here right now are basically your x-axis is time. So you will see that the incident happened for around 1/5 of a second, and the y-axis is your frequency. So this is a spectrogram. And the two panels are for the two LIGO detectors, LIGO Hanford and LIGO Livingston. And the color denotes the energy of this event. Okay? So you will hear two different sounds. One is the actual sound, and one is an amplified one. So I think at least in the amplified one, you heard this whoop, whoop sound, okay? And that's a characteristic property of this signal, and it's called chirping. So everything that has happened here is a result of this entire dynamics. So what happened is, and what we just said, and the story that I built right now, is from just a 1/5 of a second. So what happened is two 30 solar mass black holes, they spiraled, and when they radiated out their gravitational wave, and as they were radiating out their gravitational wave, they started coming closer to each other. The spiral became faster, and they merged. And when they merged, there was a shoot in the frequency and the amplitude, and that is what you get, the whoop sound. Just to answer your question, so I will not get into the details here, but what we do is from various theoretical simulations, what we create is templates, and so we create templates for, say, different masses, different parameters of a black hole, or different parameters of a neutron star, and we match these filters with the observed detection. So if I have a time series, so basically a waveform in the time axis. So what we do is we match it with all our waveform, and we find out the best fit. And from that we can get the best fit parameters of this particular event. There are also things done which are not model dependent. From that also, actually this event was very nice because we could actually pick it up by actually seeing it visually. The another set of interesting events which happened in 2017 was that of the merger of two neutron stars. Now neutron stars are so-called dead stars. So it's basically the dead core of some very massive star. So our sun will not be a neutron star when it dies. It will be a white dwarf, but a much massive star will become a neutron star. The only thing is here what you saw is not just emission of gravitational wave, but emission of electromagnetic waves in the entire window, electromagnetic spectrum. And from here, we can actually learn a lot about nuclear matter and also about astrophysics. But I'll not talk about this one. I'll quickly go to this subset of black hole and neutron star event, which we observed in the first and the second observational run of LIGO. So in the first and second observational run, we had 10 binary black hole mergers and 1 neutron star merger. So in this picture, you see like a subset of those binary black hole. The blue color is that for the binary black holes. So your y-axis is basically the masses in solar mass, and the blue colors are the binary black holes which in spiral to form the remnant black hole. The purple ones are the X-ray binaries, which binary black holes, X-ray binary black holes which have been found in our own galaxy. Similarly here, you see the only neutron star merger which happened. The question mark is because we still don't know whether it's what happened at the end of the merger, whether it was a black hole or it was a hypermassive neutron star which changed into a black hole. We still are debating about it. And these are all the known neutron stars or pulsars which has been observed through various electromagnetic spectrum, either radio or X-ray pulsars or something. So one thing which worried a lot of extra astronomers is like most of you see the masses of the black holes that has been observed are above the already observed X-ray binaries, X-ray binary black holes. So they were quite skeptical about the result for a long time. So the other interesting thing is interferometers are like microphones. So unlike, say, a radio telescope, which has a very good angular resolution, interferometers doesn't work like that. It basically works like our ears. So our brain does it for us. That's why we don't know. But we actually, if there's a sound coming from one side, we actually move our head a bit to localize the sound. Similarly, interferometers are exactly like that. So a single interferometer is very bad to localize the event. And so we need multiple interferometers. So we have 2 interferometers right now in US, which is in Hanford and Livingston, and one in Virgo in Italy. And Geo 600, so Virgo has an arm length of 3 kilometers. And there's also a Geo 600 of arm length of 600 meters in Germany. There's LIGO-India, which is coming up in 2025, I guess. And Kagra in Japan should be operational by the end of the year. So all that I said right now, you can understand there's a lot of physics which goes into it and a lot of work. But the most important thing is, apart from all the electromagnetic spectrum that we had till now, all the electromagnetic observations we had till now, this is a new window. And a lot of new information can come up from here. So a lot of, as I said, more than 1,000 scientists are working on different areas of this physics. And what I am particularly interested in is to understand the theories of gravity, if you can test the theories of gravity from gravitational waves. So I'll give a brief understanding of why this is important. So I'll go back to the mid-19th century when we all knew about Newton's theory of gravity. And Urban Lebeau and John Adams, who were both mathematicians and astronomers, what they individually predicted the Neptune using just pen and paper. So nobody knew about Neptune at that point of time. They knew about Uranus, and there was a discrepancy in the observed and the predicted orbit of the Uranus. And using that and Newtonian mechanics, they could actually pinpoint that there should be a planet or a body further away, and they actually knew the position of it. So when they told their astronomer friend to look at a particular direction, they could actually find Neptune around the same region. So that's the power of Newtonian mechanics. So this is the reason why we still study in our school level, because it's very, very important. But Urban Lebeau went on and he started studying about celestial mechanics, and he found a similar kind of discrepancy, which is called the precession of the Mercury, which you can see in this particular video or GIF, that the elliptical orbit is actually moving along the plane, and this is called the precession of the Mercury's orbit. And what he understood is there should be another planet in between the Sun and Mercury, and he even named it Vulcan. But no one now could actually find it until 1915, when Einstein gave his theory of general relativity, which was precession of the Mercury's perihelion was the first proof of Einstein's theory of general relativity. So what I'm trying to say here is, as a scientist, you always have a scope to still investigate from the new data and the new observations that you're having. So, and why? And so the first question is, why should we look beyond GR? Everything works. Why should we look beyond GR? The first answer is, why not? Because, as I said, you always have to find out what new that you can learn from the data. If you stop answering questioning, then you will stop doing research. But there are actually some valid theoretical reasons why we go beyond GR. The reasons, and I don't want to actually get into all these things individually, but the thing is, there are a few problems in the theory of general relativity. Like we see that our universe is expanding, and it's actually expanding at an accelerated rate. And this can only happen if we have something called a dark energy, which has a negative pressure, something which we don't know what it is. So, do we really want to believe in that, or do we think that there is some other theory at a different scale? Like Newtonian theory is right up to a particular scale. It's just at a different scale, GR comes into the picture. So, is it at a different scale when the curvature is very high or the energy is very high? Is the system going? Is the gravity theory going to go for another change? The other thing is, we consider GR as a four-dimensional system. Now we know quantum theories of gravity, where like string theory, where people say that the scientists claim that we live in a very higher dimensional gravity. So all these things, plus you have so also if you have a quantum theory of gravity, and if you come down to the classical level, you always have some extra fields, and not just the gravitational field that you have in GR. So there are many fundamental reasons to look beyond GR. The only thing is, GR has passed all the experimental tests till now. The word of caution is, most of this are done in the weak field limit. Like what? Like the solar system test. Like a pulsar going around another neutron star. These are all very so-called weak field limit. It hasn't worked. It hasn't been experimented in the strong dynamical fields until now. So with gravitational wave, we can do that. So now this is what I was talking about. This is your time series data from Hanford, Washington, and Livingston, Louisiana. And and from theory, assuming that GR is right, we can generate waveforms. Okay, so which is say given here. These are numerical relativity waveforms, which are generated assuming that GR is right. So now what we can do is, we can subtract this from this, or maybe the other way around, and find a residual. And this residual is within the experimental error, which is within like the 4% error. So now we know that at least for an event like this, if there is some alternative theories of gravity, it should be at a very, very small level. Okay. There can be other tests, like so this part, the initial part is your in spiral. So when your body is moving, you have your initial part here, and then the peak comes when it actually merges, and then once it merges, it forms a black hole, which is in an excited state, and then it releases gravitational wave as it rings down. So it's called the ring down part. So now, if we can find out what are the individual masses or the component masses of the black holes from the in-spiral part, use our theory to get what will be the final mass of the black hole, and then we can independently measure the mass of the black hole from the ring down part and see whether it matches or not. If GR is right, it should match. If there is anything else, then it should not match. But again, with an experimental error, it has matched. But this is not the end of the story. because we haven't got a lot of data, and there's a lot. These are experiments. There are a lot of errors which are coming into the place. So people are now trying to test GR via different methods. And here I will end my slide saying that it is true that what we have done till now, what LIGO have done till now, is mind-boggling. But what is going to come now, right now the third observation run is going on, and we have observed more and many more black holes. So what I feel is what the data that we will get after the data, the information that we are going to get in the years to come will dwarf all this. And this is a very interesting time, and I really want you guys, like the young minds here, to get into this and, I don't know, observe more gravitational waves and do physics with it. Thank you. So for the test system that I used, the Earth mass system, what was the strain that you, like what is the order of magnitude of the strain that you observed?
10⁻26.
Okay, that's right. Can anyone say the energy that is being radiated out, the power? Yeah.
Here.
200 watts.
So that's also right. Also, don't answer in chorus because only one can get the T-shirt. Okay, how many questions? 3, right? 10. Okay. What else? Anybody knows the LIGO-India site? Take the mic. Mumbai. Anyone better than that?
Yeah. Rural Maharashtra.
Sorry?
Rural Maharashtra.
Calcutta? West Bengal.
No.
Hingoli
Yeah.
in Maharashtra.
Yeah. Okay, great. Okay. So, who is the scientist who said that space-time tells matter? Black T-shirt there. Okay. Can you please?
Professor Wheeler.
Okay, perfect. It's good when do you know the first name or you just said Professor Miller, which is a good trick. Okay. Can I ask a question which is not LIGO related? So, which independence? What is the Independence Day that we are celebrating today? Like, what's the number? Can I get the? Okay.
73rd.
Oh, perfect. Okay. I actually missed this out. But if anybody knows the maximum strain, the order of magnitude maximum strain which was observed by the first LIGO event.
10⁻⁻21.
Perfect, thank you. Just to mention again, I actually missed it out, so I must say, so the highest strain that was observed was 10⁻⁻21. And now, this can also be a question. Now you know that the arm lengths of the LIGO detectors are 4 kilometers. So can you tell me what is the order of magnitude of delta L that you're measuring here?
4 into 10⁻⁻18 meters.
That's perfect. So just to give you the people who have were struggling with these numbers, just to give you an idea, and this can also be a question in a way. Do you know that the size of a nucleus of an atom? Maybe -15. Okay, I got an answer already. Sorry. So it's basically 1,000th of it, and that's what they're measuring. 1,000th of the size of the nucleus of an atom. Or there's someone who puts it in this way: the closest star to us is Proxima Centauri, apart from sun, apart from the sun. Now, the deflection is like that of the width of a hair, if we consider that to be our length. Okay, so that's really mind-boggling. Anyway, how many questions are left? One more. Perfect. Where is the Virgo site? Italy. Sorry?
Italy.
Okay, perfect. Thank you. If now you have any questions.
Yeah, I wanted to ask that the lowest measurement is the Planck's length, as we have assumed. So the gravitation, how do we measure the
Lowest measurement of what?
Hello?
Lowest measurement of what?
The Planck's length is there. Okay, so how we measure the gravitational waves which are lower than the Planck's length? This is 10 to the power minus 34 10 to the power minus 34 meters.
That's the lowest step possible.
So we are not measuring that, right?
No, this is the lowest, like how we measure it at such a small scale.
So we are not measuring that, right? We are measuring of the order of 10 to the power, as I said, 10 to the minus 18, right? So as I said, like the Earth-Sun system, it, whatever it produces, we can't measure that. So it's not like we are measuring everything. We are measuring something which is within our sensitivity curve, right? So that's why even when it's in spiraling, it's not within that frequency band, and that's why we are not measuring that. Once it comes, it creates enough impact for us to measure it, or else it will like be below the limit where the noise is.
Is it possible for space-time to tear? Because it's like a fabric. It takes part in the cosmic events. Even because it's impossible for it to tear.
So there are theories, I guess, but for that you have to have a violent explosion for something like that to happen, right? So you can have like something like a wormhole in your space-time. So yeah, but for me it's still popular science, I guess.
So I have one question. Many of these solar events, etc., are being measured in terms of billion years or billion light years and so on. Distance of very high order or time is of very high order, right?
What kind of events?
Say for example, you take this formation of solar event. You talk about 100 billion years, right? My question is, even we think of a distance from here to nearest black hole or whatever. It could be of the order of several, millions of light years. The question is, when we tell about some of these distances or some of these times, how precision are we? I mean, how accurate are we? What is the delta are we talking about?
So I don't think I can give you a right answer to that exactly how much, but why we can actually say that it's this amount, this away, or like as I said, it's like 1.3 billion light years away from us. That comes because of the fact that like from the waveform, and we can get a lot of information out of that waveform, which tells us like it's coming from which direction, and what's the actual energy which should have been there, which has propagated. As I said, it goes as 1/r, right? So from all those calculations, you can find out the distance to this particular event, like what we have observed, and how far is this thing. Okay. So there are multiple degeneracies here because now we have found out the masses. So if you look at that equation of the energy, you have the masses, you have the distance, and everything. So if you have found out the masses, now you can find out the distance in a way. So it's kind of that kind.
With the analogy that you had just provided of the LIGO event to a ear listening, as we know that ear has three-dimensional, detecting sensors in X, Y, Z directions. Can we think of having similar arrangement for LIGO also, in which we currently have X and Y axis? Can we have a Z axis as a like a pit or kind of a well that will have some sort of detector, such that when you get the waveforms, you can get the combination of X and Y or X and Z or Y and Z, kind of getting some more information? Is that a possibility, kind of?
So I think it's possible from multiple detectors if it's oriented in a different direction, rather than going away from this L-shaped interferometer thing.
So you said that any accelerating mass produces gravitational waves, right? So is it like it is losing energy on while it is doing so?
So it's not about just gravitational waves. Accelerating electrons also generate ripples in the electromagnetic field.
EMFs, yes.
And so that's basically your energy radiating out, right?
Yeah.
So yeah. So your answer is yes.
Okay. So another one, accelerating from which frame of reference? So if anybody is accelerating at the same rate, so he will see it as a moving with constant velocity. So or at rest. So does he also sense gravitational waves?
So it's in the source frame. So acceleration in the source frame. It's when the binary system is considered to be the source. So you are measuring in that local frame. Okay. So in relativity you have concepts of source frame and local frames, right? Where if you are in if there's a frame of reference which is accelerating away from you, so that's a different frame of reference than us. So now say if an object is coming from a very far away distance, it gets redshifted. So what we measure here, say, is everything which is redshifted, like the masses are redshifted masses and all these things. But since we know the distance and all this thing, or the distance, we can say what is the mass in the source frame. Similarly, when you're saying accelerating bodies, I mean always in the local frame or in the source frame. Does that answer your question? Or?
Yeah. Okay.
Hello, sir. Regarding this interferometer, what is the thing to have the clarity, something like that? So the thing is that how can we exactly find the without any errors? Is it the place or the arm length? What decides the parameter? Like for example, you have stated that there are going to come in India, somewhere in US. So is it the arm length that measures accuracy, or the place, the disturbances which reduce it?
See, the thing is, we have a limitation to the arm length, right? Because we can't make it as big as we want. If we make it as big as we want, it's much better. Because you have to understand, it's delta L over L. It's a ratio. Okay. So, and that's the reason why, if you have heard about LISA, which is a space-based mission, which is going to go up in 2030s.
Okay. So,
and then you have like a parsec scale kind of a arm that will detect different kind of events, because it will be in a, like, you have gravitational waves happening in different frequencies, and different experiments or different instruments measure different gravitational waves.
So it is better to have the widest, like the arm length to be
as big as possible. So that's why, like when I talked about Geo 600, it's a 600-meter gravitational wave and nobody uses it. But it was like a precursor kind of a thing to see whether things work. So
this gravitational wave detected on 14th September. So have you found out when it happened? Is it like
I told you, like it happened like 1.3 billion years ago. So
excuse me, I have another question. See, when you work on this, theoretical modeling, would you, somewhere I saw that you talked about gravitons, right? So would you model this as a movement of gravitons at any time, or you will be talking about gravitational waves, or then you will switch between gravitons and waves?
So it's a very different concept. So if you have gravitons, and this has been okay, we are talking about GR, which is massless graviton, which basically says that the propagation of the gravitational wave will be at the speed of light. When you have a massive graviton, this will be different. And this has been, so that's basically the difference. It has nothing to do with gravitational waves. The speed of the gravitational waves will have something to do with the mass of the graviton, but not like the gravitational wave itself. Secondly, the observation of the binary neutron star, which happened in 2017, has put a big constraint on the mass of the graviton, because now it is assumed that the gravitational wave travel at the speed of light. Because since for neutron star we could actually localize the event, so there has been other electromagnetic radiation from this particular event. So we actually know the speed of the gravitational wave, okay, and that's why the theories like massive gravity, which considers gravitons to have a particular non-zero mass, are kind of ruled out or highly constrained. Okay, does that answer your question?
No, actually I was thinking that this, like how we have photons in electromagnetic waves, they are dual and they have existence like that.
Now you're going in the quantum gravity level. We are not in the quantum gravity level. We are in the classical level still. So what we are observing is in the classical level. So that's why we are talking about classical theories of gravity. When I'm talking about extended theories of gravity, which are influenced by string theory or quantum theories of gravity, but I'm always talking about them coming down to the classical level. They don't come down to GR. They come down to something plus GR, or GR plus something. GR plus some extra fields, like some extra scalar fields, and we call it like scale intensive theories and all these things.
Okay, let me remind you folks that there is also a prize for the best question from you to the speaker. So he'll be choosing the speaker. Okay, best question.
Sir, so the entire LIGO setup is inspired from Michelson interferometer, right? So we have studied that for a consecutive interference, it is del x equal to n lambda. Okay. So we use laser for laser as a source in Michelson interferometer. Here also we use laser, but as that del x determines the accuracy of the instrument, if we actually reduce the wavelength, that is increase the frequency of the source, suppose say if we use X-ray as a source, is that possible to increase the accuracy of the LIGO setup?
How are you saying that? Why it will happen? So for everyone now we use infrared, but why you're saying that?
Replacing laser with X-ray source, will that improve the accuracy of the LIGO?
I don't understand why you're saying that, because here what is happening is, so you basically need, and why low frequency is used is because of the fact they interact less, I think. And here the frequency of the laser beam, I don't think is very important, apart from the fact of from an engineering point of view.
Okay.
Because
in Michelson interferometer, we actually that rings which forms in the screen is determined by the wavelength of the source, right? Like that determines the accuracy of that minimum separation between the concentric rings is determined by the wavelength.
So what you're talking about is a double slit experiment or something like that.
Michelson
but here what is happening is basically if the phase of the light is such that if the arm length is same, there will be no light. That's it.
Yeah.
Okay. Now if there is a change in the arm length,
yeah,
then that will generate some output on the photodiode, which will convert into an electric signal.
Yeah.
So it has nothing to do with, at least I
Will that
can't
improve
understand.
the sensitivity of LIGO? If we increase the frequency of the source which you use in LIGO?
I'm not getting why, but because here you're not creating any fringe pattern on it.
Yeah.
That's not the case here. So
That correlation you are doing it right to find how much how much the arm length has changed. Like the way we
that
did-
will just lead to an output.
Yeah.
Say it is in some form of a energy output. So the energy output won't matter what frequency you're taking.
Okay.
That's
So maybe we can use radio waves also for LIGO. Like
yeah, as I said, like I think the choice of what frequency band is used, it depends, I think, more on from engineering point of view than actual science. That's my understanding, I guess. Because infrared is used because they interact less with the environment.
okay, what laser is being used there? Infrared.
So, you're measuring the gravitational waves from the black hole, mergers and neutron star mergers and all. So, any binary system generates these waves, right? So then, and also in the beginning you said that this moon and the earth is a binary system. So why don't you just measure those gravitational waves? Because even though the black hole's waves are actually stronger, still they have to travel over a long distance, so the energy actually decreases.
The thing is, if you calculate the energy that is being created by Earth-Moon system or a Earth-Sun system, it's very, very small. So even if it's not traveling a long distance, it is not creating enough to be detected by the present sensitivity of the gravitational wave. Maybe at some point we will be sensitive enough to observe something like that. But right now, even these events are so far away, but they generate so much of energy that even if they travel this particular distance, there's still enough to create a detection for us.
So when we talk about gravitational waves, one of the incentives for us to really detect them is the hope that they will give us information about a system that light otherwise can't. So A, what has LIGO inferred so far about the gravitational waves we've detected? And B, what do we expect to find really in terms of information of the system?
So the second question first. So we already have the information of the system. That, like, say, by information I mean, like, if you're saying, say, the masses of the system or the spins of the system.
Okay, so my second part is not necessarily related to the black holes that we detected. The hope in the future is that gravitational waves will give us an insight into early universe, right? So when we talk about that stage, what is the information we hope that it will give us about during the dark ages where light wasn't present? Essentially, gravitational waves will give us some information about it.
So as you mentioned, it's it's not just that it's a different it's a different window. It's not just that where light is not coming from, you are getting it. It's also a different window. So you are verifying a theory from a different point of view. Okay. So I can give you an example. Right now, I'm working on a project related to dark matter and trying to constrain the fraction of dark matter that is there in this universe. Okay. So it has been done to death by from electromagnetic waves point of view. But there are all this the models that are being used are the constraints that have been put are very much model dependent. What we are trying to do is we are doing the same thing from a gravitational wave point of view, and we are seeing better results that we can put, and it is not very much model dependent.
What are these results? Like, I understand you're getting new results.
Yeah.
What specifically are you inferring from?
So there are multiple things. So as for even if we are studying the universe, the cosmology, then you are getting the Hubble constant
from the gravitational wave point of view. So it's not like when you have an experiment, you do it just with one apparatus. If you have multiple apparatus, you should do it. And things like this, which you don't have in a lab, you have to use as many apparatus as you can use. So now people are getting an independent measurement of, say, the Hubble constant using gravitational waves. So similarly, what we are doing is trying to get an independent constraint on the fraction of dark matter from gravitational wave in a particular regime where we are sensitive to. Similarly, so another thing is, like at least what I showed is, till now, GR has been tested. What we can do till the data we have, GR is still the theory. Like there are things like polarizations, which I talked about, like the plus, like the squeezing and that's the plus and the cross polarization. If you have a different theory of gravity, say if you have a scalar field, then there will be some other polarizations, and we haven't observed it. But also the problem is there are not enough detectors to observe polarization. So we can't say everything right now because we are still in the beginning stage. So, but till now GR is still the theory. So if you have like all the waveforms from the numerical relativity which uses GR fits properly, and the residuals that you get are within the experimental bar. So there are all we get to know a lot about the theory of the nature of the theories. Secondly, so also from neutron star, that's another thing. That's a thing about multi-messenger astronomy. So you're doing both gravitational wave and electromagnetic observation at the same point of time, and that gives you that gives you constraint from both these things. So now you can actually use that to constrain the Hubble constant again, because gravitational wave gives you some certain informations. Electromagnetic gives you some other informations which doesn't fall into that the same parameter space, and you can use that. Now you can use, like, you have different parameters to constrain things, so you get better constraints if you can use multiple observations.
According to string theory, gravitational force can communicate between dimensions, and now because gravitational waves have been detected, theoretically and experimentally it's correct. So doesn't that mean that higher dimensions don't exist?
Absolutely not. So you can constrain in a certain way, but the thing is, again, the problem is we live in a classical, what we are doing are classical observations. Okay, so if you can prove that certain certain theories at the classical level gives a certain probe or certain particular feature, and you have disproved that, then you can say that, okay, string theory or any other quantum theory of gravity is a problem. But you can't claim about dimensions. I don't think you can claim about space-time dimensions from, or constraint space-time dimensions from gravitational wave observations.
If higher dimensions, as in like 5 dimensions, 6 dimensions, do exist, or according to M theory, there are 11 dimensions, and if string theory is actually right, then shouldn't the gravitational force leak into other dimensions as mentioned in string theory? But then it's not. So doesn't that mean higher dimensions do not exist?
See, the thing is, whatever string theory gives, you have the brain, you have the bulk, right? So you have to, when you're talking about classical theory, you have to, like, if you have a consistent string theory, it should come down to at the classical level on the brain and tell me what is there on the brain. So people try to do all these effective field theories and all these things, which try to get an idea about this quantum theory of gravity at a classical level. So you have to, what I'm saying is, you have any quantum theory of gravity, because these are not quantum observations. So you have any quantum theory of gravity, it should come down to a classical level to something. Now that something should give should give you some certain observational probes. If you can prove or disprove that, then you can say something about it. That's my understanding. I might be wrong, but I'm not a string theorist.
Sir, I have a question. So there was a small lab set up over there, right, using this laser beam which you detect, right, gravitational waves, using light pulse to try to observe this gravitational waves because of this interference pattern and all, right, using that as a basics of photonics. But see, whenever you introduce a camera, the light behaves differently. That's the basics of photon. The interference pattern itself, the light behaves as a particle when you suddenly observe it using a camera. Or when you remove the camera, it behaves as a different thing. That is the quantum mechanics happening over there. In observation itself, we have a lot of different parts. You switch off the camera, it behaves differently. Nature behaves differently. Right? The consciousness of the whole universe itself changes when you don't observe it. So when we are observing using experimental way, right, using LIGO or light, or observing the gravitational waves or something, what is the error introduced when you don't observe it? Will the gravitational wave will be behaving a different way? Because we are observing everything using a camera. When you switch off the camera, how is the universe consciousness?
I don't think I followed your question properly, but are you asking like what kind of like does it boil down to the fact that
what will be the pattern of the gravitational wave, the original essence of the wave itself, when you don't observe it? Because we are observing, we are introducing the camera and all these photonic instruments. Because light itself behaves differently when you don't observe it, right? It has its own wave pattern. Because we are using light as a fundamental essence to detect something, but light itself behaves differently. What is the error introduced in finding the actual gravitational pattern? You say something as X for gravitational pattern. I may say that it may be a Y if you don't observe it.
So I think the question boils down to the fact that how sensitive are these instruments? Because
not sensitive, how effectively we are saying one entity as a gravitational wave, but it may be a different altogether when you don't observe it using electronic instruments or photonics, which actually based on that when you start observing, see, I am seeing you. If I don't observe, you may be different. Right? That's what quantum mechanics says. Right? You are a particle when I observe you. If I switch off my camera, you will be different. That's why the magician transportation concept comes, right? The teleportation, all those things comes, right? When you don't observe, magician makes you think and suddenly he can. There are two things of magicians, like one they do it by faking you, other one definitely by making our camera switch off, they teleport using a wave. These are all the higher things. So in that way, gravitational wave, when we don't observe using these experimental parameters that we set up here, how it is measured? Is there any model that comes up without observing using traditional camera or whatever the super camera you use it?
See,
without light interference.
As I said, there's gravitational waves everywhere, right? Okay. Now, and the feature of the gravitational wave is it stretches and compresses distances. Now you need to have some sensitive instrument to see that. Okay. Now, what you are saying is how sensitive my instrument is. Now, when your light,
the question is if my instrument is introducing an error in
that's the thing. We make sure up to the level that we can that the instrument doesn't make any, introduce any error. Or there are other terrestrial sources. Everything we produce gravitational wave. The waves in the ocean produces gravitational waves. So we make sure that we are not observing that. There are many ways that they do it, and I don't know the entire detail, but some of the things are the mirror these are very polished to the nanometer scale. The beam, as you said, the light which is propagating here, because it's not vacuum, it scatters. That's why we are seeing it. There it's not scattering, because it's the best vacuum that you can ever get. They are also they also keep a measure the seismographs which actually control the mirror. Whether if there's something happening, they actually can control the mirror. Also, the mirror is basically hanging. So there are a lot. I'm not an engineer and I don't understand instruments very well, but.
My only question is the introduction of the camera itself spoils the nature of the light.
But it depends on which kind of camera you're using.
No, of course. So any photonics, anything observed on the light, right? The light pattern itself changes. But we are using light as an instrument to record something.
True.
So when the light pattern itself changes by observing it, how effective are we finding a solution? That's the
here the thing is, when you're saying all these things, it has a lot of conditions involved. When you're saying I'm using this kind of instruments, what are the factors in those instruments which are creating the problems? So I'm sure they're trying to reduce those things.
Are we taking care of that model to eradicate?
Yes, for sure.
So, how do you actually check if LIGO is working before an astronomical event? Like, you can't wait for two black holes to collide and then check whether LIGO is working in the first place, right? So, how do you do that?
So, there are things called calibrations which are done, and also like when LIGO was not observing, and LIGO is going on for around like 20 years or something. LIGO was not observing, and people used to get bored. So there were situations when some of the big shots used to just generate some fake signals to see that. And when you're generating fake signals, what you mean is, I know all the parameters, I know what it will happen, and but I will not tell it to anyone. Can these people actually go and do all the data analysis and do everything and get the exact parameters or not? So then those are the checks and balances that you always take.
Yeah, and one more thing. How do the lengths of the arms, I think it's 4 kilometers, right, one arm. So how does it actually impact the accuracy? If you increase the lengths, then will it make it more accurate?
Yeah, because you see the same thing as who mentioned that, I think him, that say if my strain is maximum strain is 10 to the minus 21, okay, if my length is 4 kilometers, which is 4,000 meters, it comes down to measuring 10 to the minus 8, 40 to the minus 18 meters. Now if I have a bigger length, if I have say 400 kilometers, then I'm going down, then I have to measure 2 orders less, which is easier.
How do you differentiate between a global seismic event to gravitational waves? Because basically you have two arms which basically shift, right? And if it's a global seismic event, then it will happen all over the place. So both the detectors would detect it compared to a gravitational wave.
So both the detectors, we want all the detectors to detect.
Yes.
Okay. And that's the only, for the first event, both the LIGO Hanford and LIGO Livingston detected it. So in 2017, there were triple detector detections, like also Virgo detected the same event. So we want both the detections. What you're saying is the global seismic effect is basically what we call the continuous wave. So it's basically, say, CMB, or the cosmic microwave background, actually also produces gravitational wave, and we can absorb it. Which we should, like Planck and all these other cosmological experiments have observed it. Can we also do it for us, it will be just a continuous wave coming from every direction. So here it's not like we will understand that it's not from one particular direction, but it's coming from everywhere. And that is what we call the continuous wave. And we can actually do a lot of physics out of that. So we don't want to kill it.
How do you actually measure the amount of energy in a gravitational wave?
I showed the equation, right? That comes from theory.
Yeah, but if it's just delta L by over L, then it will be dimensionless. But energy is not dimensionless, right?
But you also get, as I said, you collect the data in this photodiode, which you convert into this electric signal, and from the signal you can, so it's in frequency bands and everything, so you can calculate the energy from there.
So, but energy is basically capacity to do work or something like that. But gravitational waves do not do any work, right? So how can you say that the gravitational wave has energy?
It is not doing any work. It is coming from 1.2 billion light years to here, so it's doing a lot of work.
Yeah, but it does not actually produce any displacement. Like it stretches and then it the body which is stretched and compressed, it comes back to the original position again, right? So then it does not do any work.
Is this the force into displacement thing that you're talking about? No, so it doesn't work like that. So these are transverse waves, which are also electromagnetic waves. So they basically propagate in the direction perpendicular to the direction of the gravitational of the wave, and so this propagation happens. It's not a continuous thing. It's not a it will propagate out.